Hey everyone, and welcome back to this series on elementary probability and statistics. In the last discussion, we discussed three important probability mass functions, in particular the geometric, the binomial, and the Poisson distributions. In this video, we're going to be discussing three other probability mass functions that have a variety of applications, in particular the hypergeometric, the negative binomial, and the multinomial distributions. Let's get started. Alright, so let us suppose you have a population of size capital N that contains k possible successes in that population, and you select a simple random sample of size little n from that population P. Let x represent the number of successes that are in that sample that you have drawn. So let us draw a little picture to sort of simulate what we are looking at here, and this is going to be associated to a hypergeometric distribution, this random variable x here. So let us assume we have a population size, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So let's say capital N is going to be equal to 10, 11, 12, 13, 14, and 15. Okay, so we're assuming that there are 15 values in our population here. And what we're going to be doing is selecting a random sample out of this population here. So this bigger large box is going to be P, and this smaller box is going to be our sample S. And of course, the sample must be simple and random. So in this particular sample, our sample size contains 1, 2, 3, 4, 5 values. And we see that the number of values that are successes in our entire population is 1, 2, 3, 4, and 5. Okay? So if we look at this particular sample, and we let x represent the number of successes in our sample, so we clearly see that the maximum value that this x can have is going to be equal to the maximum possible values that you can have that can be successes, right? So the maximum value that you can have in this particular sample that are successes are 5. But of course, we can make our sample smaller, and then this value x is going to be bounded above by the number of the number of values in our sample. So we have two restrictions that are going to bound this value of x, but we clearly see that the minimum value of this value x is going to be equal to 0, and that's going to be regardless of the scenario that we're going to be looking at. Right? But I'll explain this maximum value of this random variable x in a little bit more detail once we look at a particular example. But let us now define the distribution that is associated to it. So one can show via a combinatorial argument that the distribution associated to this random variable x is going to be equal to k choose x multiplied by n minus k times little n minus x all over capital N little n. And all of these are combinations, of course. So what exactly are we looking at here? So capital N choose n's, this is pretty much the number of sample combinations. And this k choose x, that's going to be the number of success combinations. And if k is the number of possible successes and capital N is the number of values in our population, that means capital N minus k is the number of failures that could happen in our population. And if little n is our sample size and little x is the number of successes in our sample, that means little n minus x is the number of failures in our sample. So that means this is the combination associated to the number of failures with respect to the population, and k choose x is the number of combinations associated to the number of successes for a population, right? So we have successes, failures all over the total number, so we're pretty much looking almost like a binomial distribution, but we're not focusing on probabilities, we're just pretty much focusing on the size of E divided by the size of S approach here, right? So it's a very nice alternative way of doing probabilities, but this is what we call the hypergeometric. So a hypergeometric distribution, right? So you can use the hypergeometric every time you know capital N, little k, and little n, and you know all the values inside of our sample are independent, and that's guaranteed by the SRS criteria that I stated below. So remember, since x is a random variable, it's going to have an expected value as we can anticipate. So this is going to be equal to n times k divided by capital N. So that's the expected number of successes that we anticipate to be in our sample. And of course, the variance for the hypergeometric is actually a little bit more difficult. So this is going to be equal to the expected value, little n times k over capital M. And then we're going to have a couple more terms, capital M minus k over n, and then capital M minus n over capital N minus 1. I'm not going to prove these values here, but this should be familiar to you if you sort of think about and analyze this from the binomial distribution perspective. And this, I'll leave it to you to sort of explore what that actually represents and where it comes from. But again, you can generate the moment generating function for this random variable and get these formulas if that makes you happy, right? So let us take this time to go into a couple examples of how we can use the hypergeometric distribution to solve real world problems. All right, suppose you have a village of 27 people and you know that 5 of them are sick. Let us assume you select a simple random sample of size 7 from that village. What is the probability that more than 2 of them are sick? So if we sort of focus on this last term, what is the probability that more than 2 of them are sick? Clearly, we're defining x to be the random variable of the number of people that are sick in our sample, right? And this particular problem is asking the probability that more than 2 of them are sick, right? So this is going to be equal to the probability that x is equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 5 plus the probability that x is equal to 6 plus the probability that x is equal to 7 plus the probability that x is equal to 8 plus and so on, right? So no big deal there. So what do we have here? So we have that the village contains 27 people, so that's going to be our capital N value. We're selecting a sample of size 7, so this is going to be our little n value. And the number of people that are sick in our village is 5, right? So 5 of them are sick, so that's going to be our k value. So since we're selecting a simple random sample from this population, this is going to be a hypergeometric random variable, this value x here, okay? So let's look at this infinite series here because we have the probability that x is equal to 3 all the way out to infinity since we're looking at a more than 2 type of scenario, right? So keep in mind that the possible number of values for this particular scenario is going to be 5. Therefore, we cannot have that and we cannot have this since k is equal to 5. So the possible number of successes in our sample cannot be more than the number of successes in our population. Moreover, since we're selecting a sample of 5, yes, technically the probability that x is equal to 8 can also not be included in that range. But moreover, the probability of x and onwards cannot be true because we have a sample of size 7, right? So the sample size is equal to 7, therefore we cannot have 8 successes in a sample of 7, or more than 8 for that matter, right? So all of these probabilities here are equal to 0, therefore we're only going to be interested in the probability that x is equal to 3, 4, and 5, right? So that means the probability that x is bigger than 2 is just going to be equal to the probability that x is equal to 3, plus the probability that x is equal to 4, plus the probability that x is equal to 5. So remember that k is equal to 5, capital N is equal to 27, and little n is going to be equal to 7, I believe, right? Yes. All right, so this is a geometric random variable, so we're going to be using that in a little combination types of formulas, right? So I'm just going to write out the probability that x is equal to 3 form. So we're going to have 5 choose 3, right? So 5 choose 3. So that's the number of values in our sample, right? No, it's the number of possible successes over the number of successes that we want in our sample. And then if we do 27 minus 5, that's the number of failures in my population. And 7 minus 3 is the number of failures in my sample. And then we're going to have 27 choose 7. That's the number of samples that we could have, right? So number of successes in our sample, number of failures in our sample with respect to the population, and also number of samples. And similar goes for px4 and px5, right? So once you work out this combination, so that's going to be equal to 5 choose 3 multiplied by 22 choose 4 all over 27 choose 7. So keep in mind that 5 plus 22 must be 27 and 3 plus 4 must equal to 7, else it's not true. All right, and we're still needing to find px4 and px5 So once you actually work out that, you're going to have approximately equal to 0.0824 plus the other two values, and your final answer will be 0.0913. So there's a 9% chance that more than 2 people in your sample of 7 will be sick. And that is an application of the hypergeometric distribution. Now let us look at another distribution that can often be used to solve real-world problems. All right, so suppose you have a sequence of independent Bernoulli trials, and you continue the sequence until R successes occur. Let X represent the number of failures in that sequence. So just the prelude of this explanation should reminisce from another distribution that we discussed, in particular the geometric distribution. That is, you have a sequence of failures until you get your first success. So if we have a sequence of independent Bernoulli trials and we continue the sequence until we get our first success, so R is equal to 1 is going to correspond to a geometric random variable for X, right? So what we're actually going to do now is we're going to continue until we possibly get more than one success, 2, 3, 4, 50, and so on, right? And X is going to represent the number of failures in that sequence. So let's look at a couple scenarios that sort of illustrate what we're looking at here. So let us look at the scenario where, let's actually look at the case where R is equal to 3. So we could have failure, 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 success, failure, failure, success, failure, 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 and success. So since this is the third success, we're going to stop this sequence. So what we're going to be looking for is the probability that X is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 failures in that sequence, right? So this next distribution is going to answer that question. But this is not the only scenario that you have for R is equal to 3 successes. For example, you could have failure, failure, success, success, failure, 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 bunch of failures, success, right? So in this particular scenario, let us assume we have 2 failures there, and let us assume we have, say, 72 failures there, right? So in this particular scenario, what we're interested in is the probability that X is equal to 74, right? Like, what is that equal to, right? For still, R is equal to 3. Right? So R is equal to 3 is going to be a parameter, and the number of failures is going to be a random variable that we're going to be looking for. So one thing we need is, of course, the probability of success. We're going to be denoting this by a little letter p, similar to how we did for the geometric and the binomial distribution. And yeah, that's pretty much what we're going for. Keep in mind here that if we're looking for the probability that X is equal to 10, those 10 failures can be in any of these positions that we want. So we're going to be looking for a combination as usual, but it's not going to be a combination for all of the events because this last event is going to be fixed. So we're actually going to be looking at one less of the combinations compared to, say, the binomial distribution because this last one must be a success by definition. All right, so let us look at the distribution that is going to be built upon, and I leave it to you to sort of justify why this distribution is what it is. So this is going to be equal to x plus r minus 1 all over r minus 1. So these r minus 1s is associated to the number of successes that are permuted in our combinations, right? Because if we have 3 successes, that means these 2 s's could be in any of these positions that we want. So that's pretty much why we're subtracting 1 from each of them. So we're going to have 1 minus p to the power of something and then p to the power of something, right? So remember, r is the number of successes that we continue this sequence until, right? So the power that is associated to p must be equal to r, and x represents the number of failures in that sequence. So x must be the exponent on 1 minus p. So this distribution isn't quite the binomial distribution, but it's slightly a variation of it, which is where it sort of gets its name from in terms of the negative binomial distribution, where x is a negative binomial random variable. Okay, so as usual, it gets a expected value formula. So the expected value is going to be equal to p times r over 1 minus p, and the variance of this random variable is going to be equal to p times r over 1 minus p, the quantity squared. All right. So those are the two formulas that you can generate from the MGF for a negative binomial random variable, which I'm not going to go into. But these are some of the basic principles you need to understand before we actually get into an example. So let us assume you have that, and let's just do a real life example on how you might use the negative binomial in real life. All right, suppose you play an arcade game or some other type of game where there's a winning losing type of scenario, such that the likelihood of winning is 43%. If you play until you win 3 times in a given day, what is the probability that you lost 10 times? Right? So there's no statement of independence. So since we don't know anything more about this game that we're playing, we're going to have to assume independence in order to get any type of approximation for the probability for this type of problem. So let us assume that each game is independent. So if you lose a bunch of times, you're not going to be tilted and your likelihood isn't going to change. Um, and let us see if we can figure out how we can solve this problem. So we're going to play until you win 3 times in a given day. So if we're going to use our negative binomial distribution, r is clearly going to be equal to 3. And we want to know how many times we failed in that sequence. So clearly the value of x is going to be equal to exactly 10. We could do at most 10 or at least 10 or any variation of that, but this problem just says the probability that we lost 10 times at that sequence, right? So for example, we want to know all the variations of success, success, failure, failure, 5, 6, 7, 8, 9, 10, right? So that would be our 10 failures that we're looking at, and there's our 3 successes. So the things that are going to be permuted in terms of the combinations are going to be those 12 values, right? So it's going to be 13 minus 1, which is x plus r. So notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. Well, 10 failures and then 2 successes. That's going to be 12. So total number of sequence of values is going to be 13. So it's going to be 13 minus 1, and we're going to be permuting our 2 successes, I guess you could focus, or permuting the failures. It's the same exact problem. Okay, so we're going to be using our negative binomial distribution. So let's just bring up our formula again. So r is equal to 3 and x is equal to 10. So the probability that x is equal to 10 is going to be equal to 10 plus 3 minus 1. So that's going to be our 12 values. And we're going to be focusing on our number of successes that are being permuted. So since the last one is not being permuted, that's going to be equal to 3 minus 1. And you can verify with the formula that I stated before that this is exactly what's going on here. So we have the probability of failure. So what's the probability of success? So the probability of success was 43%. So the probability of failure is going to be 0.57. And how many failures do we have? We have 10. And how many successes do we have in the sequence? We have 3. Okay, so this formula will give you the correct answer. And if you work those combinations and exponents out, you're going to get approximately 0.018998. So about a 2% chance that you actually lost 10 times in that game sequence, assuming that you stopped when you got your third. So that would be an example of the negative binomial distribution. Now let's take a look at our 6th special probability mass function, known as the multinomial distribution. All right, so suppose you have n different objects to select from, each with probabilities of being selected p1, p2 down to p capital N, where the sum of those probabilities is equal to 1. So before proceeding with this explanation, you can sort of begin by thinking of this as a bag of marbles, each of which have a variety of different colors in them. So you can have a bag of red, blue, yellow, white, black, green, purple marbles in that bag, and if you know how many of each different colors there are, then you can calculate the probability if you were to draw one marble from that bag, then the probability of selecting, say, a blue marble would be equal to, say, 5 over 36, if there was 5 blue marbles and 36 total marbles in the bag. So now instead of selecting one, we're going to be selecting a sample of little n different objects from the population. So we're going to select 17 of those marbles, and we want to know how many red, how many blue, how many green, and so on marbles are going to be in that sample size m. All right, so we're going to let xk be the random variable that represents the number of objects selected in that sample event, right? So we have a variety of random variables, not just one here. So there is a slight difference between this and the others. So it's more like a generalization of, say, the binomial distribution. So XR would be the random variable associated to the number of red marbles. XB would be the associated variable for the number of blue marbles in the bag, and so on, right? So one clear property is that the sum of these x values, so clearly k is going to range from 1 to m, so all the different types of marbles in that bag. So xk is the number selected, so this total number must be equal to the sample size. So that's an obvious restriction that we must have. So what is the probability distribution associated to this? So this is going to be called the multinomial. So the multinomial distribution. So it's a generalization of the binomial. So instead of only having success and failure, you have type 1, type 2, type 3, all the way down to type n. All right? So the probability that capital X1 is equal to little x1 and capital X2 is equal to little x2, all the way down to capital Xn is equal to little x capital M. So those are capital N's, by the way. So what is the probability that we have 5 red, 2 yellow, 3 brown, 5 white, 2 black, 7 pink marbles in our bag of 50 or something like that, right? So the total number, the sum of x1, x2, xn must be little n, or sample size, and this probability is going to be equal to little n factorial, our sample size, all over x1 factorial times x2 factorial, all the way down to x capital N factorial. So this formula should look familiar from our examples when we were rearranging letters that had some repetition. So if you want to sort of build where this formula comes from, that's definitely a very good place to start. And then we're going to be multiplying this by the probability of marble 1 times the number of marble 1s we have. Probability of associated to selecting the second marble times the number of second marbles we have. And this is going to continue all the way down to the probability that we get the nth marble to the power of n x capital N. Right? So we only have one sample size implementation in this formula, and that's the numerator of this permutation type of thing here. And this entire distribution is what we refer to as the multinomial distribution. So very beautiful and very simple, actually, if you sort of think about it. So, of course, we have several different random variables, x1, x2, xn, so we're not going to be graphing this unless, for example, x1 and x2 are the only variations we have. But then we could use this via the binomial distribution if that was the case, right? So unless you want to do 3D graphs or multidimensional graphs, you probably wouldn't consider the graph of this because we have x, y, z, w, t, a, b, c, and so on, right? So the expected value of random variable xk is going to be equal to n times pk. So that comes directly from the binomial distribution. And the variance for this random variable xk is going to be npk 1 minus pk. So again, this is a mirror image of the binomial expected value and variance, but it's different for each of the types of things that we have in our particular sample. Okay, so that is the introduction to the multinomial distribution. Now let us look at a particular example where we could use this in real life in terms of the multinomial distribution and how to use it. All right, consider this example. Suppose you visit a zoo and the percentage of each animal is shown in the pie chart to the left. Select a random sample of 10 animals to visit. I've made this pie chart, of course not drawn to scale, but very simple because I've only chosen a few animals: zebras, giraffes, monkeys, and a bigger category, birds. You can make this more realistic or study your local zoo if you have one, and do this type of example as, say, a research project or something. So let us assume we want to know the probability. So we're going to name these categories. I'm going to name them in a counterclockwise fashion. I'm going to call this, say, x1 for zebra, x2 for giraffe, x3 for monkey, and x4 for birds. Okay, so we're going to be selecting a random sample of 10. So I want to know the probability that, say, x1 is equal to 1, x2 is equal to 3, x3 is equal to 2. So if I give you these three numbers, you should be able to figure out what this next value is. So we have 1 plus 3 is 4 plus 2 is 6. That means this must be equal to 4. right? So remember that these numbers must sum up to your sample size of 10. So what is the probability that in my sample of 10 that I get one zebra, that I'm able to visit one zebra, 3 giraffes, 2 monkeys, and 4 birds in this zoo visit? Okay. So this is going to be equal to what? So we have our sample size factorial on the top, and then we're going to have 1 factorial, 3 factorial, 2 factorial, 4 factorial on the bottom, and then we're going to have our probabilities raised to each of these numbers. So the probability of visiting zebra, or 15% of the zebras, is 15% of the zoo is going to be zebras, so it's going to be 0.15 to the power of 1. And then we're going to have 0.25 to the power of 3. Then we're going to have 0.20 to the power of 2. And then finally 0.40 to the power of 4, right? So once we work out this type of problem, we're going to have about 0.03024. So the probability that we visit this particular structure of animals will be 3%. Now, if you were to be asked what is the probability that in your sample you could have one zebra, 3 giraffes, um, and at most 2 monkeys, right? So if I say at most 2 monkeys, that would be 2 and that would be 4, that would be 1 and that would be 5, and that would be 0 and that would be 6, right? So when you do inequalities, there is a little bit more trickiness associated to it, but that would be one variation that you could easily do, right? Whereas I fix 2 of them, I vary the third based on some inequality because that third is going to force the number in that next sample, as long as my sample size is fixed, of course. So that would be an example of how we can use the multinomial distribution and a couple variations that you possibly could investigate as well. So in this video, we discussed 3 more different types of distributions: the hypergeometric, the negative binomial, and the multinomial distribution, which adds to our list of PMFs, which were preceded by the geometric, binomial, and Poisson distribution. So with these 6 distributions, you can definitely solve a lot of different types of problems. There are other PMFs which we're not going to get into, at least not now. So I hope that all of these give you some ideas of how you can actually use probability mass functions in real life. So stick around and we'll do some practice problems just to make sure you understand the material that we discussed today. See you around.